Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the properties of gas mixture. Consider a gas mixture that consists of 2 kg of nitrogen and 3 kg of carbon dioxide. The total mass of this mixture is 5 kg. How is this done? Well, we simply add the mass of each component. This example suggests a simple way of evaluating the extensive properties of a non-reacting ideal or real gas mixture. Just add the contributions of each component of the mixture. Then the total internal energy, enthalpy, and entropy of a gas mixture can be expressed respectively as. By following a similar logic, the changes in internal energy, enthalpy, and entropy of a gas mixture during a process can be expressed respectively as. The extensive properties of a mixture are determined by simply adding the properties of the components. Now, reconsider the same mixture and assume that both nitrogen and carbon dioxide are at 25 degrees centigrade. The temperature of the mixture is, as you would expect, also 25 degrees centigrade. Notice that we did not add the component temperatures to determine the mixture temperature. Instead, we used some kind of averaging scheme, a characteristic approach for determining the intensive properties of a mixture. The internal energy, enthalpy, and entropy of a mixture per unit mass or per unit mole of the mixture can be determined by dividing the preceding equations by the mass or the mole number of the mixture. We obtain these properties per unit mass involve mass fractions, and properties per unit mole involves mole fractions. Try to find the data of internal energy of the mixture. Following the relations shown here, we have the answer of 560 kilojoules per kilomole. The intensive properties of a mixture are determined by weighted averaging. The weight factor might be mass fractions or mole fractions. The relations are exact for ideal gas mixtures and approximate for real gas mixtures. The only major difficulty associated with these relations is the determination of properties for each individual gas in the mixture. The gases that comprise a mixture are often at high temperature and low pressure relative to the critical point values of individual gases. In such cases, the gas mixture and its components can be treated as ideal gases with negligible error. Under the ideal gas approximation, the properties of a gas are not influenced by the presence of other gases, and each gas component in the mixture behaves as if it exists alone at the mixture temperature and mixture volume. This principle is known as the Gibbs-Dalton law, which is an extension of Dalton's law of additive pressure. Also, the properties of an ideal gas depend on temperature only and are independent of the pressure or the volume of the ideal gas mixture. The partial pressure of a component in an ideal gas mixture is simply Pi, where P mix is the mixture pressure. Evaluation of delta U and delta H of the components of an ideal gas mixture during a process is relatively easy, since it requires only a knowledge of the initial and final temperatures. Care should be exercised, however, in evaluating the entropy change of the components, since the entropy of an ideal gas depends on the pressure or the volume of the components as well as on its temperature. The entropy change of individual gases in an ideal gas mixture during a process can be determined from. Notice that the partial pressure of each component is used in the evaluation of the entropy change, not the mixture pressure. Partial pressure of component I and state 1 is. Partial pressure of component I and state 2 is. When the components of a gas mixture do not behave as ideal gases, the analysis becomes more complex because the properties of real gases depend on the pressure as well as on the temperature. In such cases, the effects of deviation from ideal gas behavior on the mixture properties should be accounted for. When real gas mixtures are involved, it may be necessary to account for the effect of non-ideal behavior on the mixture properties, such as enthalpy and entropy. One way of doing that is to use compressibility factors in conjunction with generalized equations and charts developed in Project 5 for real gases. Consider the following T-ds relation for gas mixture. This is an important result because this equation is the starting equation in the development of the generalized relations and charts for enthalpy and entropy. This equation suggests that the generalized property relations and charts for real gases developed in Project 5 can also be used for the components of real gas mixtures, but Tr and Pr for each component should be evaluated using T-mix and P-mix. This approach just described is somewhat analogous to Amagat's law of additive volumes, which holds exactly for ideal gas mixtures and approximately for real gas mixtures. Therefore, the mixture properties determined with this approach are not exact, but they are sufficiently accurate. What if the mixture volume and temperature are specified instead of the mixture pressure and temperature? Well, there is no need to panic. Just evaluate the mixture pressure using Dalton's law of additive pressures and then use this value as the mixture pressure. Another way of evaluating the properties of a real gas mixture is to treat the mixture as a pseudo-pure substance having pseudo-critical properties determined in terms of the critical properties of the component gases by using case rule. The approach is quite simple and the accuracy is usually acceptable. As shown in the figure, it's difficult to predict the behavior of non-ideal gas mixtures because of the influence of dissimilar molecules on each other. Okay, that's all for this task. Thank you very much and see you next time.